All right, so we're going to talk a little bit more about DISC method and some variations on what we learned last time. And I think it's best to just start with an example this time. So the region bounded by the graphs of y equals root x, y equals 2, and the y-axis is rotated about the x-axis. What is the volume of the resulting solid? So the first thing we want to do, whenever possible, is to sketch this. So this would be the graph y equals root x, and then y equals 2 is a horizontal line through the y-axis at 2. And we're rotating again around the x-axis, which means we're taking this area, this sort of curvy triangular area, rotating around the x-axis to get a sort of a, what would that be, a cylinder with like a parabolic scoop taken out of the middle of it. And we want to calculate the volume of that solid. But before we calculate the volume, we're going to want to find the area of this solid that once I rotate around the x-axis will give me the volume. So the area of an object is base times height. And the base of my object is along the x-axis. So I need my bounds for integration. Well, on the left-hand side, that's not a problem. Because I'm bounded by the y-axis, I know that my lower bound is at x equals 0. My upper bound I'm not so sure about, but I do know that it's defined wherever y equals root x and y equals 2 are equal to each other. So I'm going to set them equal to each other. Root x equals 2, and figure out what x would have to be. It would have to be 4. And so my upper bound then is 4. So that covers the base, the length of the base. Now I need the length of the height. And remember, the height is my radius. So I'm going to use my function squared to give me my radius. Well, that's easier said than done. In this case, you can see that I'm going to have to use one function, y equals 2, and subtract from that the other function, y equals root x. And what I'll be left with is this green region, which will have the area that I want to rotate around the x-axis. So that's also easy enough to do, and I think I'm kind of ready to even set it up. First, though, let's remember our formula for volume. Volume equals pi times my base, a to b, and my height, which is the radius function, squared dx. So this particular volume then is pi times the integral from 0 to 4. My radius function is a combination, right? So my radius function is my big function, 2, minus my little function, root x, squared dx. And now it's just a bunch of calculations. Pi, integral 0 to 4, 4 minus 4 root x plus x dx. Antiderivative, pi times 4x minus 4, let's see, x to the 1/2, x to the 3/2, so it's 8 x to the 3/2 over 3 plus x squared, evaluated on the interval from 0 to 4. So I have pi, 4 times 4 is 16, minus, x to the 3/2. So that would be 4 to the 3/2. I think I'd rather take the square root first. So the square root of 4 is 2 cubed, which equals 8. So this is 8 times 8 is 64 over 3 plus 4 squared is 16. Oh, look at this. I made a mistake here. 4 squared, the antiderivative of x is x squared over 2. So 4 squared is 16 divided by 2 is 8. And I don't have to worry about the minus 0 because each of these will zero out. So that's pi times 16 plus 8 is 24 minus 64 over 3, which equals pi times 3 times 24 is 60, 72, take away 64 is 8 over 3, and better written, 8 pi over 3. So that's the area for the shape rotating this green, that's the volume for the solid of rotating this green area around the x-axis. Suppose instead, though, I had wanted to rotate around the y-axis. I would have gotten an entirely different solid. Around the x-axis, I would get this kind of cylinder with a parabolic hole cut in it, but on the y-axis, I would get one of those trumpet shapes. And I would have to make some changes to my formula. Notice that on the rotation around the x-axis, my delta x, right, the sum of my delta x's is my base. So from a to b dx is my interval of integration, a and b on the x-axis, leaving my y value, or my height, my radius, to be my radius function squared. But if I were rotating around the y-axis instead, notice that my interval of integration, my delta y's, would be along the y-axis, and now my radius runs perpendicular to that along the x-axis, or horizontally in the opposite direction. And so that changes up my entire function if I rotate around the y-axis. My volume this time, I'm still doing a rotation with a radius, and notice the top of this trumpet would be a circle. So I'm still doing my pi r squared, but now my boundaries of integration are going to be a and b on the y-axis, and my radius function is going to be with respect to y. So my radius function r of y is still going to be squared, and then my delta y's, which is dy, is where I'm integrating. So it's going to switch the formula up, or it's going to switch out the variables. It's going to change my evaluation, but it doesn't really change the process. So let's do this. Let's label it that we're doing this with a y-axis rotation. And our volume equals pi times, well, the bounds of integration. Well, let's look. I'm rotating the green area around the y-axis, which means my radius is solid all the way through. So I don't have to do the one function, take away another function. On the other graph, my radius, notice in this brown region, the radius, this wasn't part of the radius, it wasn't part of my area. So when I wrote my function, I had to take the whole amount and then take away this bottom part. But when I'm looking from the perspective of the y, doing a rotation around the y, I don't have anything that has to be taken away. My radius is connected to the y-axis completely, and so I don't have to worry about that. So my bounds of integration then are from 0 to 2, and my function is just whatever this curve is from the perspective of the y-axis, which means my f of y. Well, that's easy enough to figure out. If y equals root x is my function, my f of x function, right? So I have f of x equals root x, then solve for y, and I get y equals, not sure where I want to write this, so x then equals y squared. So all I did was have to solve my function, this curve, which is the one I want, this curve, as a function of y is x equals y squared. So I have y squared, which has to be squared because that's my radius function, and then dy. Well, that's just pi times the antiderivative from 0 to 2 of y to the 4th dy, and that's just pi times y to the 5th over 5 from 2 to 0, or 0 to 2, and so that's pi times 2 to the 5th is 32 over 5 minus 0, so that's 32 over 5. Notice though I got a different result than I did in the first one. Shouldn't be worried about that because I actually got a different shape. The first shape was sort of, I'm not entirely sure I can sketch this, I'm going to give it a shot, was sort of a cone, or excuse me, a cylinder with a parabolic hole cut into it, which of course I can't draw. And then the second shape was a bugle shape. So they don't look the same, or they don't have the same area, volume, because they're not the same shape. All right, time for one more example, I think. The region bounded by the graphs of y equals the quantity x minus 1 squared plus 1 and y equals 2 rotated about the y-axis. So the y-axis, our formula then is the volume is pi times the integral from a to b of, this time my radius function is in terms of y, needs to be squared dy. So I think first things first, let's graph it so we can get a picture of what we're talking about. First function is a parabola, vertex form, so I know I have a vertex, it's upward facing, and the vertex is at 1, 1. And I know that there's a y-intercept at 0 minus 1 squared is 1 plus 1, 2, which is convenient because the other graph, or the other function, is y equals 2. And then using symmetry, I know that this other point is, well, from 0 to 1 to 2 is at 2, 2. And before I start looking at the picture, I'm going to go ahead and solve this function for x because I know I'm going to have to anyway because my radius function is in terms of y. So I have y equals x minus 1 squared plus 1. Subtract 1 from both sides. Y minus 1 equals x minus 1 squared. So x minus 1 equals plus or minus the square root of y minus 1. And so x equals plus or minus the square root y minus 1 plus 1. And I think I'm going to break these apart and color code them and rearrange them. So there's the version where x equals 1 plus y minus 1, or the square root of y minus 1. And then there's the version where x equals 1 minus the square root of y minus 1. Okay, and the reason for that is from the perspective of the y-axis, 1 is here. Of course, 1 is always there. But from the perspective of the y-axis, this orange one is the x value is 1 take away the square root of y minus 1. So this side, from the perspective of the y-axis, because remember, this may be a function in x because it passes the vertical line test, but it is not a function in y. So I have to separate it into two separate functions. Okay, and I've color-coded the part. This pink one being 1 plus y minus 1, or the square root of y minus 1. All right, so we have enough information, I think, to put the whole thing together. So we have our volume equals pi times, well, first we need our limits or boundaries of integration. So remember, this is with respect to y, and so we want to know what this distance is. This is our delta y, and it's easy to see that our boundaries are from 1 to 2. So on the y-axis, I'm only going to integrate from 1 to 2. Then I need to find my radius function with respect to y, and I have two of them in this case. I have the one that on this boundary, my radiuses are going to lead me to the pink function, right? So I'm going to get the pink function, which is 1 plus the square root of y minus 1 squared, right? So that's that area wrapped around the y-axis. And then I have to subtract out of that. Remember, we subtract out the brown part. So I have to subtract out of that the lower radius, which is the y minus. So I'm going to subtract away 1 minus the square root of y minus 1. And that has to be squared as well because it's a radius, so it has to be squared. dy. Okay. I think we're there. We've put it together, and now when I put all of this together, when I take the outside radius and the inside radius, that's going to give me this area here, the green area. That's my total radius with respect to y. Okay, let's calculate. I'm going to take a little bit of a cheating step just for time's sake. I've already done this offline, so this equals pi times the integral from 1 to 2 of 4 square root y minus 1 dy. Okay, then integrate 4 pi on the interval from 1 to 2 of y minus 1 dy. Quick substitution for this, super easy to do. You end up with 8 pi over 3 times y minus 1 to the 3 halves on 1 to 2, on the interval 1 to 2. And that gives us 8 pi over 3 times 2 minus 1, which is 1 to the 3 halves, which is 1, minus 1 minus 1 is 0. Love that. And so 8 pi over 3 is the area for this shape wrapped around the y-axis, and I am not going to even try to draw that for you. By the way, this method has its own name, the washer method. And it has its own formula. There's an O in there. The washer method, it has its own formula as well. I don't find it easier to use or easier to work with. I think setting it up by using a picture makes more sense to me, but I'll show you the method anyway. It says that the volume can be calculated as pi times the integral from a to b of the outer function, so the bigger radius in this case of y, because I'm just mirroring this function. So the outer radius, the pink one, take away the inner radius, and evaluate it, which is exactly what I did here. I just did it by setting it up logically. There's an analogous version. So suppose you have, now let me use it, I'll color code again with the pink and the Y. So say I have some outer radius and some inner radius, and I'm evaluating this. I want to evaluate this area wrapped around the x-axis, I would be able to set this up as the volume equals pi on the intervals, let's say 0 to b, of the outer function, which is going to be a radius of 2, right? So the outer function would be this entire pink area wrapped around the x-axis. That gives me a volume. So their outer radius with respect to x. And I'm going to take away the inner radius, since I'm wrapping around the x-axis. The inner radius, man, the fan on my computer is loud today. And I'm evaluating or integrating on the variable x. And so the washer method is just another way of writing something that you can do logically, or you can do by applying the formula. Either way is fine with me.